In this video, we're going to look a little closer at the binomial distribution. So here we have a description of the binomial distribution. Suppose the probability of a single trial being a success is P, then the probability of observing exactly K successes in N independent trials is given by this formula. Here we have N choose K, which when you expand it out becomes this expression in terms of factorials. So this is the formula to compute the probability of getting K successes in N trials. So if you wanted to know the probability of getting one success, K would be 1. 2 successes, K would be 2, etc. Now they give us a little more information down here. It says the mean, variance, and standard deviation. Well, I'm not going to discuss the variance or the standard deviation, so we can ignore those, but I think the mean is important. So the mean of the binomial distribution, the expected number of successes in N trials, is given by N times P. So you take the number of trials and multiply by the probability. Now there's some important things to check when dealing with the binomial distribution. When does it apply? So to make sure you can use the binomial distribution, you should really check all these things, make sure they all apply. The trials must be independent. So the outcome of one trial should not influence the outcome of another trial. So this would be satisfied if we're doing something like rolling a die. When I roll the die, each time I roll it, the outcome of one roll doesn't depend on the outcome of a previous roll. If I'm choosing people where some percentage of them, maybe 40% of people own pets, the fact that I choose one person that owns a pet doesn't influence the likelihood of the next person I choose owning a pet if I choose them randomly. Something that wouldn't be independent is if I'm drawing marbles from a bag. So if there's maybe 10 marbles in a bag and I draw a blue one on my first draw, well, now the likelihood of me drawing blue on my second draw has changed because there are less blue marbles in the bag now. I just removed one. So those would be trials that aren't independent. So we need to make sure that the trials are independent if we're going to use the binomial distribution. Secondly, the number of trials, N, has to be fixed. It's always the same. Right? So we're doing exactly the same number. We're imagining just a fixed number of trials. Right? Rolling the die 8 times. That number 8 doesn't change. Part 3, each trial outcome can be classified as a success or a failure. So there's really only 2 things we're looking at. Either I roll an even number or I don't. Either the person I choose owns a pet or they don't. I have a success or a failure. Just 2 possible outcomes. And that's why we call it binomial. Bi means 2. And part 4, the probability of a success, P, that's the probability, is the same for each trial. So every time I roll that die, I have the same likelihood of getting an even number, say. Or every time I choose a person from the population, the likelihood that they own a pet stays the same. Okay, so let's go down here and look at this example. The probability that a random smoker will develop a severe lung condition in his or her lifetime is about 0.28. Part A, if you have 4 friends who smoke, are the conditions for the binomial distribution, binomial model satisfied? Well, let's look up here. It says that the first thing here says the trials are independent. Well, look at this statement here. It says you have 4 friends who smoke. Are they independent of one another? No, they're actually related to one another. So this actually violates the first condition of the binomial distribution. So we cannot use the binomial model to model this problem in this case. So no, the individuals are not independent of one another. Okay, so let's go down below. Suppose these 4 friends do not know each other and we can treat them as if they were a random sample from the population. Okay, so now we're saying, okay, well, suppose they don't know each other, so they really are independent, right? So now we can go down and answer some questions. So now the binomial model is satisfied. Part B, how many would you expect to develop a severe lung condition? Would you expect? Well, that's the expected number of people who develop a severe lung condition among these four. Well, for that, we use the mean. The mean is also known as the expected value. And the formula for mean is n times p. Okay? So let's look at this problem. You have 4 friends, so n is 4. And the probability is 0.28. So the expected value, the mean, is n times p. So it's 4 times 0.28. And that comes to 1.12. So I would expect 1.12 out of 4 people to develop a severe lung condition. Now you might say, well, how can that be? How can you have 0.12 of a person? Well, yeah, but if you can extend this. So if I had 400 people, I would expect 112 of them to develop a severe lung condition. So this really does have relevance. Let's look at the next question. What is the probability that none of them will develop a severe lung condition? Okay, well, here we're looking for the probability of 0 successes. What would that be? Well, the probability of a given number of successes is given by this formula right here. All right, so what we're going to do is just plug in these numbers. So the number of successes I'm having here is 0. So I'm going to have n choose k is going to be 4 choose 0 times p to the k times 1 minus p. So 1 minus this is 0.72 to the n minus k, which is 4. I have 0 successes and 4 failures. This is the probability of a success. This is the probability of a failure. So what is this? Well, what is 4 choose 0? 4 choose 0 is 4 factorial divided by 4 factorial times 0 factorial. That's just using this expression for n choose k. Right? All right, well, 4 factorial and 4 factorial cancel off. 0 factorial is equal to 1, so we just have 1 divided by 1. That's 1. So this quantity right here is just equal to 1. Anything raised, any non-zero number raised to the 0 power is 1, so we have 1 times 1. And so really it's just 0.72 to the 4th power is our answer. And that is 0.2687. That's the probability that none of them will develop a severe lung condition. Let's go to D. What's the probability that exactly 1 will develop a severe lung condition? That's probability of 1. Well, the formula says that's 4 choose 1, 0.28 to the 1, 0.72 to the 3. I had 1 success and exactly 3 failures. Probability of success, probability of failure. Okay, well, what is this 4 choose 1? That's 4 factorial divided by 3 factorial times 1 factorial. Okay, well, write that out. It's 4 times 3 times 2 times 1. That's 4 factorial. 3 factorial is 3 times 2 times 1. And 1 factorial is just 1. So a lot of this stuff cancels. So I just have 4 times 1 divided by 1 times 1. That's just equal to 4. Okay, so this guy right here is just 4. So I have 4 times 0.28 times 0.72 cubed. And when you compute that out, you get 0.4180. Okay? The last question. What is the probability that no more than one will develop a severe lung condition? No more than one. Well, no more than one means one or less, which means we're looking at the probability of 0 or 1, which we know becomes the probability of 0 plus the probability of 1. And we just computed those. Probability of 0 is this, probability of 1 is this, and when you add them together, you get 0.6867.